Continue on with learning target 8A, area between curves. We left off in the last video by having you guys try these two problems on your own. Both of them were a U substitution. I'm going to leave my full solution up here for you guys. If you have questions, please reach out to me during office hours. If you'd like to, right now might be a great time to pause the screen so you can check each of your work on both of these. Okay, let's move on and look at some more graph examples. So this one is still not calculator active. I know you guys can see my calculator on the left-hand side of my screen. We will be using it later on, but for right now, we are going to do this one by hand. So we have a graph this time, and they gave us two functions. F of x is 2x squared minus 6x plus 4, and g of x is 4 times cosine of pi x over 4. And they say R is the region bounded by the graphs of f and g as shown in the figure to the right. Find the area of R. This is an old AP problem. This is how you guys are going to see that they are phrased. So they're giving us the graph, but they're not actually telling us which curve is which. So there's two ways to do this. The first way is you could think about what the shapes of each of these graphs look like. So f of x is a parabola. Because the leading coefficient is positive here, since I have a positive 2, then I have a parabola that is facing right side up, so it would look like a smiley face. So f of x is actually going to be this function right here. So why don't we go ahead and label that for our reference. So f of x is going to be this bottom function. G of x, if I think about what the graph of cosine looks like, cosine starts up at 1 and it dips down, or starts up at its amplitude, and in this case its amplitude is 4, and then it drops down from there and it would keep continuing that wave curve. So our top function for this guy is going to be g of x. Now if you were not sure on which graph is which based off of the shapes of these graphs, I think the best thing would be to test a point in between the two and see which one gives you a larger value. So we are bounded between 0 on the left side and 2 on the right side. So I would pick a value for x in between those. Be mindful of the fact that pick something for x that you can plug in and actually find cosine of that value. So probably x equals 1 would be a good idea. Okay, to find the area between these, as a little recap, I need my bounds, and I need to know which one is my top curve and which one is my bottom curve. We've already established that g of x is the curve on top, and f of x is the curve on the bottom. So the next thing I need is my bounds. Well, they are intersecting right here, and that coordinate pair is at 0, 4. So my x value for this guy is going to be 0, and my y value will be 4. So I have 0. Oh, hold on, let's erase that craziness with the pen. So here, this coordinate pair, again, for our reference, is going to be 0, 4, and then on the right side over here I'm at 2, 0. Because we're integrating with respect to x, I care about the x values on this. So we will get the integral from 0 to 2 from g of x minus f of x with respect to x. Now, if this were calculator active, I could absolutely leave this as my setup here because g of x and f of x are well defined in the function for me. I would type this into my calculator and figure out what the answer is. Since we're going to do it by hand though, we are going to sub in the functions and then do some actual U substitution to integrate this guy. So coming back here, we have the integral from 0 to 2. G of x is the 4 cosine piece, minus f of x is this entire quadratic. Make sure you have your parentheses around it with respect to x. I'm going to distribute the negative sign. So we get minus 2x squared plus 6x minus 4 with respect to x, and of course I should have my integral sign in front. Now from here, this first piece is going to require a U substitution to integrate the cosine. The rest of it is going to be a power rule. So if I'm being precise with my notation, I should actually probably split this back up into two integrals so that I can look at it from there. So the first guy will go 0 to 2 of 4 cosine of pi x over 4 dx plus the integral of negative 2x squared plus 6x minus 4 dx, and again I have the same bound since all I'm doing is breaking this apart into the piece that requires a u sub on the left and then the power rule, which I'll use on the right. Our u sub here is going to be the inside piece of the cosine, so pi x over 4. Now when I take the derivative of that, remember pi and 4 are constant, so I end up getting pi over 4 times my dx. Now to isolate this guy, I would divide through, which is the same as multiplying by the reciprocal. So I end up with 4 over pi du equals dx, and then I can reset up my u sub from here. Let me scroll down to give us enough space on this. The 4 that is the scalar in front, I'm going to pull out of the integral. So I get 4 times 4 pi, the integral as x equals 0 to x equals 2, remember these are x bounds, of cosine of u du. Now plus, this whole piece I can integrate right now, but for the sake of keeping them consistent when I integrate, I'm just going to rewrite it so that we have it as reference as we keep scrolling down the page. Okay, the last piece to do is to actually integrate this guy. So I end up with the 16 over pi. The antiderivative of cosine is going to be sine. So I get sine of u evaluated as x goes from 0 to x goes from 2, plus on this piece I can just use the power rule. So I get negative 2x cubed over 3 plus 6x squared over 2 minus 4x, also evaluated from 0 to 2. Now the last piece to do is to sub my u back in before I deal with my bounds. So we get 16 over pi sine of pi x over 4. Now plus, I'm going to rewrite the whole rest of this piece, and I'm going to group it together with one set of bounds since they're both going from x equals 0 to x equals 2. So we get our whole second integrand that we had, reducing that fraction down as we go, evaluated from 0 to 2. Now from here, I've integrated the entire thing. I have my full antiderivative, and the last piece that I have to deal with is subbing in my bound. So my top bound's going to go in first, minus my bottom bound. So for the top bound, I get 16 over pi sine of, when I plug in the 2, I get 2 pi over 4, which would be equivalent to pi over 2, minus 2/3 times 2 cubed, plus 3 times 2 squared, minus 4 times 2. Now minus, when I sub in the bottom bound of 0, all of this stuff with just the polynomial is going to cancel out, but I do sub it into the sign, so I do get minus 16 over pi sine of 0 in this case, minus, 0 plus 0 minus 0, so that's all very redundant. The last thing I have to worry about is evaluating my trig functions. Well, sine of 0 is 0, so that whole piece is going to go away, and sine of pi over 2 is equal to 1, so we end up with 16 over pi minus the 2/3 times 2 cubed, plus 3 times 2 squared minus 4 times 2 on that piece. And we have everything there. So as a little recap on this problem, I do have the graph. They did not label the graph all the way for me, so the first thing I had to do was figure out which one is the top curve and which one is the bottom curve. From there, I can set up my integral to find the area between curves. Remember, the area between any two curves is the integral from my left bound to my right bound of my top curve minus my bottom curve. So that is how I got the integral from 0 to 2 of g of x minus f of x. Since this is not calculator active, we're going to be doing it by hand. So as I sub back my two functions, the next piece I had to do was distribute the negative sign and then remember to integrate from there. Now, the first piece on the left did require a little kind of baby u substitution that I had to worry about. The right piece was just the power rule. As we continued it on, we ended up recombining it here once we subbed back our u value into the sign. And then I subbed in the top bound minus subbed in the bottom bound from there to end up with my final answer piece down here, which I'm leaving unsimplified since it is a free response. Okay, Our next problem is similar. So they're giving us a graph again. They're labeling the points on it. So I'm intersecting at 0, 0 over here, and then I'm intersecting at 1/2, comma 1. Let me erase that little mark that just got made. But what I need to worry about is which one is my top curve and which one is my bottom curve. Well, f of x is a cubic function. So if we're going to think about what the shapes of these look like, remember the graph of x cubed. If I draw it over here on the left, an x cubed graph, on that piece, let's retry that again. An x cubed graph for this guy is going to go up like a parabola, but then down here it's shifting down. So that is actually curving through there. So my x cubed graph is actually going to be the bottom piece here. So I can label the bottom graph down here f of x, since that is curving up and then growing, and then on the left side, if I had more, it would keep going down. The top graph here is sine, so that is my g of x, and the reason I know that is the sine curve starts at 0, 0, if I'm looking at one cycle of it, and it curves up, and then it would dip down, and it would create that wave function and keep going from there. Again, if you're unsure which one it is based off of the shape of the graph, feel free to test a point in between. In this case, since they're intersecting at 1/2, you'd have to pick something smaller than that, so maybe like 1/4. To go on from here, I've got to do my same setup that I've been doing. So to find the area of this guy, we're going to integrate. My first place they intersect is at 0, so that's my lower bound. They then intersect at 1/2, so that will be my upper bound, with my top curve, which is g of x, minus my bottom curve, which is f of x, with respect to x. Again, if this was calculator active, I would be good with my setup. I could type this into my calculator, see what numerical value I get out, and then write equals that value accurate to the thousandths place. But since we're going to test our integration skills here and make this not calculator active, I'm going to sub in the functions and actually integrate this by hand. So we get the integral from 0 to 1/2 of sine of pi x minus the 8x cubed dx. Now from here, 8x cubed is going to be a power rule. I do need to do a little u substitution here with the sine. So my u on this guy is going to be pi x. So in the process of finding my du, I'm going to end up picking up a 1 over pi. So I get 1 over pi du equals that dx value. Now since I'm not doing a u sub over here, I want to be proper and split this up into two integrals. So I get the integral as x goes from 0 to 1/2 equals, and then I get my sine of u, but then to replace the dx piece, I pick up a 1 over pi in front, and then my du, plus the integral from 0 to 1/2 of the negative 8x cubed dx, which I can integrate with just using the power rule. Now that both of these are ready to go, I'm going to go ahead and integrate them over here. So these guys are going to be equal to my 1 over pi. Antiderivative of sine is negative cosine, so I actually get negative 1 over pi cosine of u, evaluated as x goes from 0 to x equals 1/2, minus the antiderivative here is going to be 8x to the 4th over 4 from, again, 0 to 1/2. Now I have to be extremely careful here. I can plug in the bounds on the second piece, but on this first piece with the cosine, I have to sub the u back in first. So before I deal with the bounds, I'm going to end up getting negative 1 over pi cosine of now pi x, and since the bounds are the same, I'm going to regroup them together again, minus, now if I reduce the 8 over 4, I get 2x to the 4th, evaluated from 0 to 1/2. Now from here, because all of my u subs have been put back, I'm all in terms of x, I can sub in my top bound minus my bottom bound. So if I sub in the top bound first, I get negative 1 over pi cosine of pi over 2 minus 2 times 1/2 to the 4th, minus, now the entire second piece is going to be in parentheses, so I get negative 1 over pi. Let me just erase the division bar there, that was a little too high. So I get negative 1 over pi cosine of 0 minus 0, since when I sub that second piece in, it's going to all zero out. Now from here, I've just got to evaluate my trig functions. Cosine of pi over 2 is 0, so that piece is going away. But cosine of 0 is going to be 1, so I end up with negative 2 times 1/2 to the 4th plus 1 over pi times 1. Because cosine of 0 is 1, I got the plus sign from multiplying those two negatives there. And then this piece right here leaves us with our final answer. Now this problem actually had a part B. So part A was all the area between curve stuff, which we found by setting up the integral from my left bound to right bound of my top function minus my bottom function, subbing the values in. We had to do a little u sub over here. We ended up integrating it, subbing in stuff. I ended up with this as my final answer for the area of this region R that's up here. Now part B is a little bit of a review problem here. It says write the equation for the line tangent to the graph of f of x at x equals 1/2. So I don't need to worry about g of x anymore. All I need is f of x. So for reference down here, why don't we add that back to our paper since we can't see it from the top right now. So f of x was equal to the 8x cubed, and they want the tangent line at x equals 1/2. Well, to get any equation of a line, I need a point and I need a slope. Well, the point they gave me, the point here, if I write it, the x coordinate is 1/2, and if I scroll back up to the graph, I know that at 1/2 comma 1, that is on the graph of f of x. So I have the point value being 1/2 comma 1. Now the last thing I need is my slope. To get the slope, I need to take the derivative. So I'm going to find f prime of x here. Derivative of this guy is going to be a power rule, so the 3 comes down, get a 24x squared there. No, it's been a while since we've been taking derivatives. Now to get the slope though, this is the slope at any point. I specifically care about 1/2, so my slope value then is going to be equal to f prime at 1/2, which will equal 24 times 1/2 squared. Now, if we simplify this just for the sake of writing our final answer, I'm going to get 24 times a fourth, which ends up giving me positive 6. So I have my slope here of 6. I have my point. For a tangent line, the easiest way to do that would be point slope form. So remember y minus y1 equals m times x minus x1. Subbing everything in, we get y minus 1 equals our slope of 6 times x minus 1/2 here. And there's our final equation for our tangent line for this graph. So as you guys can see, there will be review problems that kind of get thrown into here depending on what they decide to ask on the AP test. Okay, let's look at kind of a different type of graph here that we have. So all of the examples we've seen so far, the 4 in the first video and the 2 we've looked at now, we had a top function, we had a bottom function. But that doesn't always have to happen. Sometimes we can have a right function and a left function like we have in this picture. So if I look at this example here for this picture in example 9, we're trying to find the area of this yellow region. Well, if I look at the top portion of this, I have this curve right here as the top curve, then it becomes this horizontal line, and then my bottom curve is this straight line, then it's this horizontal line, and then it's this curve. I have way too much going on the top and bottom to try to figure this out. Instead, it would be a lot easier to kind of look at it in terms of what's going on the right side here. So this entire right side of this region is this straight line, y equals x minus 3. And the entire left side of this is actually this parabola that's opening up on its side, x equals y squared. Now, we can find the area of this. It's going to be the same thing. Our difference now is that we're going to actually integrate with respect to y. So instead of thinking about this as top minus bottom, we're going to think about this as right curve minus left curve. So let's write that out for us on here. So to integrate now, we're going to integrate as y goes from some value c to another value d, let's say, of my right function minus my left function with respect to y. Okay, so everything here when I do this is fair game because I've reshifted this and I'm looking at this now in terms of y. So if I look at our first example here, we have this right curve over here on the right side, The issue is that if I'm going to integrate it with respect to y, I can't plug in the x minus 3. So instead, I need to isolate the x value and get y plus 3 equals x, and I'm going to use the y plus 3 as my right curve. So if I set up this integral now, I have my right curve as y plus 3. Oops. As y plus 3 there, minus, now my left curve on this side over here is already set up exactly how I need it. It's already in this x equals format, so I can just sub in the y squared with respect to y. Now let's worry about our bounds. So the bounds is what am I integrating on the y-axis? Well, the smallest value down here is at -1, and the largest value up here is at +1, which means my bounds are going between -1 up to +1. Similar to how when we integrated top minus bottom, we looked for vertical lines to be our bounds. Now I'm looking for horizontal lines to be my bounds on these guys. So as a little recap, it is fair game to do this if I change everything to be in terms of y. So I have my right curve over here, which was originally y equals x minus 3, but because I can't plug in the x minus 3, I need to isolate this and solve for x actually. So I got y plus 3 then equaled my x value. That's my right curve over here. Then my left curve is set up exactly how I need it. It's already an x equals y squared, so I plugged in the y squared. To get my bounds, I'm looking on the y-axis. What's my smallest y value, which is down here at -1, and what's my largest y value, which is up there at +1. Now to integrate this, it's going to be the same thing that we've been doing in terms of x. If I were to integrate x, I'd say it's x squared over 2. So if I integrate y, it's going to be y squared over 2. Plus, now when I integrate 3, because I'm with respect to y, it's going to be plus 3y minus our y cubed over 3, evaluated from from -1 to 1. Let me edit that real quick. So we're down here from -1 to 1. Sub this in, we do the same thing that we've always done. So sub in our top bound, and I get 1/2 plus 3 minus 1/3 minus sub in my bottom bound. I get -1 squared over 2 plus 3 times -1 minus -1 cubed over 3. And that right there is going to be our final answer. There's going to be no need to simplify any of it. I have everything integrated and subbed in, so I'm good to go. Okay, for our next example, I'm going to have you guys pause the video right now and you come up with what you think our right curve is and what our left curve is. Okay, setting up this graph. What we have here is we have this kind of boulder face graph, which is this g of y curve, which they told us is the 2y minus y squared. And then this other graph over here, as it curves in on the left side, we have y squared minus 4y. So what that tells me over here is that my right curve is going to be the g of y function, and my left curve over here is going to be the f of y. So when I set up my integral here, I'm going to start with my right curve, so the 2y minus y squared, minus my left curve, which is y squared minus 4y with respect to y. Now to worry about my bounds, I need to figure out where these curves are intersecting. So down here on the bottom, this is intersecting at 0, 0, and up here on the left, it is intersecting at -3, 3. Now, since my integral is in terms of y, that means I need the y coordinates here. So I need the 0 and then the +3. So my lower bound is 0, my upper bound is +3. And then I have my right curve minus my left curve. Just like we did in the last video, if I can combine any like terms, I definitely want to do so to make my life easier. So when I do this, I end up combining stuff and I get 2y plus 4y, so I end up with 6y. Then I end up with minus 2y squared dy. Now from here, let's integrate this piece. So I get 6y squared over 2 minus 2y to the third over 3, evaluated from 0 to 3. Just like we've been doing, sub in my top bound, so I get to sub in 3 first, and I get 6 over 2 times 3 squared minus 2/3 times 3 cubed, minus, when I sub in the 0, everything does 0 out, so I just get minus 0 on this piece. And then, because it's a free response, no need to simplify. I have my final answer right there for us. Okay, we're going to shift gears a little bit and go to a calculator active problem. So if you do not have your calculator in front of you right now, why don't you pause the video and take that calculator out. Okay, this is an old free response problem. They gave us two curves, f and g. They defined it by these very lovely functions that we have here, which I'm very glad we have a calculator for. They say R and S are the two regions enclosed. So R is this first region and S is the second one. They're telling us they intersect over here at 0, 2, and that they intersect over here at 2, 4. Now, I could take the time to attempt to figure out which curve is which. I have an idea, but it's calculator active. Let's let it do our work for us. So the first thing we're going to do is I want to graph these two, and I'm going to graph f of x to be my f1. So I'm going to label these for my own reference only. So this is going to be my f1 function, and g of x will be my f2 function. So if I go to my graph, or my calculator, I'll go to a graph screen. Remember, if you hit tab, f1 of x will pop up. If you've got extra things in your graph right now, please take the time to clear it. But I don't, so I'm going to start typing this in. So I get 1 plus x plus, I get e to the x squared minus 2x. Oh, I changed that. I don't know why. It's an equal sign. It should say plus. So I get 1 plus x plus e to the x squared minus 2x, and I get that curve right there. I'm going to hit tab again and graph my g as my f2, and I get x to the fourth minus 6.5 x to the second plus 6x plus 2 there. When I hit enter, I get that red graph on there. Now I'm going to move these. I can easily drag them with my cursor for us. And if you look at it, this region right here is the region that we're interested in that they gave us on the graph. So I'm going to zoom in there and use the zoom box feature to do so. So if I go to menu and I go to Windows/Zoom, I can use this zoom box feature, which allows me to choose exactly where I want to be. See how it says first corner right there? Because I'm interested in this area, I'm going to start in the top left-hand corner right here and drag around this piece. And I think I got the whole guy. I'm going to hit escape so that I don't lose it. I do want a little bit more of that, so I'm going to take the time right now to just zoom out. In case you don't get it right the first time, you can zoom out on this. So if I zoom out just a little bit, I'm going to center it though on the graph I'm interested in, and I get that piece that I'm interested in right there. So I know what this coordinate pair is because they gave it to me. It's 0, 2. And I know what this coordinate pair is. It's 2, 4. At some point, I might need to figure out what this coordinate pair is, but we'll see. Let's see what we have to do first. So the first thing it says to do is I want to find the sum of these two regions. Well, to do that, I need to know what's my top curve and what's my bottom curve. Well, let's use our calculator over here. On my calculator, this red curve right here is my f2, which is this first curve that's going up and then over. Remember, f2 is g of x, so let's label that piece on there for us. So right here, this top curve is going to be g of x, and it means that this bottom curve on the region S is going to be g of x. Likewise, f of x is the bottom curve to begin with, and then f of x is my top curve over here. If I click back to my calculator screen, we can see that f1 was in blue, which is our f of x graph. So it starts on the bottom and then it shifts to the top for the second function over there. Now, I can set up the area for R. I know what's my top and what's my bottom. I know they intersect at x equals 0, but I need to figure out what this intersection point is to finish setting up that integral. So on my calculator then, I'm going to go Menu, Analyze Graph, and find the intersection between these two. I'm only interested in this one right here, so I'm going to start slightly to the left, click, scroll over, click to undo it, and I get this feature, this coordinate pair right here. Now, I don't have enough digits to be accurate on the AP test, and I'm also going to want to store the x value so that I know what it is. So right now, to store this, I'm going to hover over it, click, go Control var, and then hit A, and then hit Enter to store it. It is now stored. I can tell that because it's bolded. If I use my little speedy calculator button and go back to a calculator screen and hit A, I should get that value that I have right there. On my paper, what I want to make sure to do is identify this coordinate pair so that I have it. So I'm going to click, kind of bubble that in, and draw an arrow to this guy. And I'm going to say, I'm calling this A comma B, where A is the value I got, 1.0328. So let's write that down over here. It's going to be 1.0328, comma. Now to get the y coordinate, I'll need to go back to the graph. It is just 2.4. I don't need that many digits on this guy because I'm not going to end up using him. I'm just writing him down as reference for right now. So they're intersecting at this coordinate pair. I am calling it A comma B, which means that later on I can actually use the letter A in my answer when I write my integral there, since I've defined it for my grader. So to set this up, I need to find two separate areas here, but because I want their total area, I'm then going to add them together. So let's start with the area for R. So this is going to be the integral from 0 to A of g of x, because that's my top curve, minus f of x with respect to x. So this first piece right here is the area of R, plus my second integral will give me the area of S, which will go from A to 2 of f of x this time, minus g of x dx. And then this second piece right here is the area of S. And because they wanted the sum of the two, I'm going to find them individually and then put them together. Now, this is not something I want to do by hand, nor will I possibly be able to. G of x I can integrate. It's a power rule. I would need to do quite a few tricks there to integrate f of x, so let's take advantage of our calculator. So if I go back to a calculator screen, I need to pull up an integral. So one way to do that, menu, calculus, numerical integral. I'm integrating from 0 to A. Because I stored my value for A, I can use A. Now to type out g of x and f of x, that's not what my calculator knows them by. My calculator knows that g of x is f2, so I'm going to type out f2, but make sure I put of x because I need an input, minus, to type out f of x, it's going to be my f1 of x dx. Now I can do these two separately and add them together, or I can just keep typing in one line. Make sure you click out of the integral before you put your plus sign. And I'm going to go menu, get an integral again, so calculus, numerical integral. I'm going to integrate from 0 to 2 this time, and I'm going to flip-flop them. So f of x is the top curve, so f1 of x comes first, minus my f2 of x dx. And when I hit enter, I get my value. Now the AP test wants this accurate to the thousands place, so I need to write down 2.004. And because this is calculator active, I can go straight and say that this whole integral that I got right there is equal to that 2.004 that I got on my calculator. And there's my final answer for the sum of those two regions that we have. As you guys can tell, there's a lot less hand lifting that we have to do on our own because we have our calculator to do most of the heavy lifting for us, but it is all about the setup. This is absolutely necessary to have down. I can't just write down the final answer that the calculator gave me, although it's correct, because if I just write this down, how do I know how I got that? It's our job as we're doing these problems to explain to the grader how did we get our answer there. And our answer is coming from setting up all of our work right here. What we had to do on our calculator were a couple things. I had to figure out where they intersected. I also needed to probably know which one was the top curve and which was the bottom curve. So I had to graph them both, find their intersection point. If you want to be able to use A, you have to define it. So I can only use a down here in my bounds because up here I made this statement where I said a comma b equals this value. So I defined a for my grader at the very beginning. Feel free to use g of x and f of x instead of having to write all of this out. It's very extra and unnecessary to do that. If they're already defined for you, might as well take advantage of them. And because I'm finding the sum of both, I do have the two separate integrals for that guy. Okay, now if you want to, at the bottom of your course reader, you can kind of see what did I do on my calculator, and you can kind of keep track of the fact that you're graphing them, finding the intersection points, and then you're using your calculator to store the x value of the intersection points. And lastly, you're letting your calculator integrate both of them for you to get the final numerical answer. Okay, one more problem. So this one is also calculator active. It's going to be a little different. So it says let R be the region enclosed by the graph over here, and the horizontal line y equals 4. Well, I can tell which one is my horizontal line. So I have y equals 4 here, and then I have this curve down here, which I'm going to label f of x. It says the vertical line x equals k divides R into two regions with equal area. So now I have some vertical line coming down the center of this. So to do that, let's draw a vertical line now. Pretty sure I can insert a vertical line. I'm not sure exactly where this is happening, but it's cutting the region into two equal segments. So I have some vertical line coming down there like that. Let's give it a different color so that we can kind of identify it, and I'm going to make it a little bit bolder for us. The next thing I have is it tells me that this vertical line is x equals k, so let's label it. So k is going to be some constant, and it says write but do not solve an equation involving integral expressions whose solution would give us the value of k. So ultimately, I want to write an equation involving an integral, or maybe more than one integral, that gives me the value for this k. What I do know is that the area over here on the left side, which I'm going to kind of put stripes through, is equal to the area over here, which I'm going to dot through. Now, it doesn't look very equal with where I drew the line, but that's okay. I don't exactly know where it goes. That's what I'm trying to figure out. What I do know, though, is the left area over here has to equal the right. So what I could do is set up an equation where I compute the left area, and I compute the right area. And since I know that they should be equal, I can set them equal to each other, and this will give us our equation that involves integrals. Because to find the area on the left and to find the area on the right, I need to do both of those. Now, you're probably wondering, well, then what do I need a calculator for if I'm not actually solving? Well, if I look at this, I can set up both of the integrals. The integral on the left is going to have a top curve of 4 minus a bottom curve of f of x. And I can do the same thing on the right. It's going to be the same thing. It's going to be an integral of 4 minus f of x dx. The reason I need my calculator is I'm missing some of these bounds. So where exactly are they intersecting over here? And where exactly are they intersecting over here? That's what I need my calculator for. So I'm going to go back over here. I am going to clear what's happening here and clear my variables. So last time we were in class, people had asked me how to clear variables. So you go Actions, clear A through Z, hit OK, and now if I type A, it doesn't know what it is because nothing's stored for it. So I did clear it correctly. If I go over here, I'm going to go Menu, Actions, Delete All. Yes, I want to delete everything. And let's graph both of these. So if I hit Tab, my first function is going to be f of x. So x to the fourth minus 2.3 x to the third plus 4, and I get that shape. Then my second function is just y equals 4, so f2 just equals that horizontal line. What I'm interested in is where do they intersect. So let's find their intersection points. So analyze graph intersection. I'm going to find this one over here, which is at 0, 4, and then I'm going to find the second one over here. Analyze graph. Slowly working for us there. Intersection again. Click to the left, click to the right, and I get 2.3, 4. Now I want to make sure I have enough digits, so I'm going to store this value. So I'm going to go Control var. I can store it as A since I cleared. I get 2.3. So let's record some of this over here on our course reader. So the point over here was, what was that, 0, 4. And the point over here, they're saying is 2.3, 4, but let's see if we have more digits. So if I go back to a calculator screen and I hit A, oh, I just get 2.3 flat. But because I need enough decimal places, I'm going to tack on 2 zeros to that. So this is now going to give me my bounds. The area on the left is going from x equals 0 to whatever this vertical line is. Now, I don't know where it is, but we're calling it k, which means down here I'm going from 0 to k. On the right-hand side, I'm starting at the vertical line, so I'm starting at the k value and going all the way to 2.300. Now, this is key and is going to be something that comes up in this entire unit, is this phrase right here that I want to highlight for you guys. Write, but do not solve. They literally mean that. Write out the equation or the expression involving the integrals, but you do not need to solve it. So there is no need to be able to solve this from here. I set up, so this will be my final answer right here. That's going to be the end for this video. I'm going to leave the last 3 problems to you on the next 3 pages in your course reader as your exit ticket for you guys to try, and then we'll talk about them.